There we go. All right, so we're going to be working with cosecant. And we are going to need to remember that cosecant is the reciprocal of which function? Sine. So this is the same thing as 1 over sine of x, right? So we're going to start with graphing sine of x. Whoop. So we're going to graph our parent function of sine of x. Sine starts at 0, or I'm going to count my x's first. I'm going to do my normal pi over 4s that we have been using. Pi over 4, pi over 2, 3 pi over 4, pi, etc., etc. 1, 2, 3, 4, 2 pi. Alright, guys. Minus pi, 1, 2, 3, 4, minus 2 pi. So sine, we know, starts at 0. Let's see, let me get my proper graph. And winds up at 0 again at pi, and at 0 again at 2 pi. And halfway between, it's at 1. So this is sine. And we're going to think about the fact that cosecant was 1 over sine of x, and we're going to be relating it to our sine graph. So what's the one thing we're not allowed to divide by in fractions? 0. So any place where we have that sine equals 0, we can't have a value. So what we're going to have is an asymptote. Every place sine of x hits a 0, we're going to put in an asymptote. So we're going to have an absolute load of asymptotes. Every place that sine of x equals 0. What are all of these asymptotes hitting on for us on this one? Pi's. So the way we're going to list it out is we're going to say that our asymptotes happen when it's pi times some number. So we're going to say it happens at pi n. Asymptote is pi times an integer. When we're looking for our points, we're going to think about 1 over these values. The one that's easiest to spot is this is happening right at 1, right? So 1 over 1 means we're going to have a point right here. Look at my chunky marker. This value here at pi over 4, that is between 0 and 1, correct? Some sort of decimal. If we do 1 over some sort of decimal, is it going to be smaller than 1 or bigger than 1?
Smaller.
Test it. So let's say that's 3/4, right? 1 over 0.75. Gets bigger, right? 1 over 1/2, 0.5. It's getting bigger, right? 1 over 0.001 gets bigger, right? So as our sine graph gets closer and closer and closer to 0, these values are getting bigger and bigger and bigger and bigger and bigger and bigger and bigger, right? So So the way we're going to draw our shape is it's going to go and approach our asymptote over here. This side is also getting closer and closer to 0. So this side is also getting bigger and bigger and bigger and bigger and bigger. So it's going to look like that. So we're not going to be like plotting specific points, like how we did our signs just with our minimums, our maximums, and our zeros. We're not going to be doing like side points on these. We're not going to find exact values. It's going to hit right at the top of our sine curve and approach the asymptotes on both sides. We got to hit this one too. So again, we have our sine happens at -1 here. So 1 over -1 is -1. So it's going to hit right at that 1. And as our sine curve gets closer and closer and closer to 0, these values get more and more and more and more negative. So they're again going to approach our asymptotes, and they're not going to cross our sine function, but they're going to look like that. So every place we have a little maxima, we're going to have what looks like a happy face parabola. And every place we have a little minimum is going to be a little frowny face parabola that approaches those asymptotes. So every place we have a -1, we're going to have a down face. Every place we have a +1, it's going to point up. So they are based very heavily off of our sine curve. We're going to be graphing sine and cosine with each of these reciprocal graphs. So very, very similarly, it's going to have a period. These are periodic functions. And it's going to be the same period that the sine graph would have had for this amount of space. So 1 upward 1, 1 downward 1, 2 pi. So our domain for the purple graph, it's not about the gray lines, it's about the purple ones. We're going to do this in an algebraic notation, not interval notation, because interval notation would be forever long, like literally infinite. So it's all real numbers except x cannot be where our asymptotes are, that pi n. So x cannot equal pi times an integer. So that's where my asymptotes are. That's why I listed my asymptotes like that, is it helps us spot the domain. Any integer. So any counting number. 1 pi, 2 pi, 3 pi, 4 pi, blah, blah, blah. That's the same way we listed it for our asymptotes, just because we noticed that these were hitting at our zeros for sine. So our range for the purple, what's our range going to be? -infinity to -1, unioned with 1 to infinity. So it's everything except for the range of sine. Though we do include the 1 crossover point. We include the -1 and the +1. We're still going to count our amplitude the same way. It's going to be how high off of that midline we are. So since this one is our parent function, our amplitude is just 1. It's how far off that midline we are. And we're still going to do left endpoint, right endpoint the exact same way. So all those same pieces. Oh my gosh, it's almost like everything was relevant. What? Since this is our parent function, our left endpoint is 0. And our right endpoint is that 2 pi. But there may or may not be transformations as we get into other weird things. What? Oh my god. Okay, so this is the parent function for cosecant. Huh? She's not pretty. I mean, technically, that's the parent function for cosecant without the sign. Technically, that's cosecant. But we graph it based off of sine anyway, so I'm going to put sine in. I will probably draw it significantly in a lighter color on the next ones because it's a little bold. Okay, but that is how we do it. So we base it off of sine. So when we start looking at transformations, we have that same transformation form. I put our transformation form up here. But really, we're going to graph sine of these transformations and graph our cosecant based off of sine. So we're going to treat it just like a sine transformation and add in our u's at the end. Okay? So let's start with our period and amplitude, those things that are kind of like easy to pull out of there. The period is still our 2 pi over b. So in this case, what is our b? 1/3. So we have 2 pi over 1/3. So what is our period? 6 pi. So that means when we are counting up, we need to be really careful and make sure that we get enough to have an entire period on our graph. So I'm just going to count by pi's this time. 6 pi is big. So I'm just going to do... That you had what? Words. Use your words. I have more glue sticks. All you need to do is ask. I have more. You don't need to, oh, I wish I had more glue. Oh, sad for me. Roll my eyes at you. All right, so I'm going to count my x-axis by pi. So I'm going to have pi, I'm going to do 2 pi, I'm going to do 3 pi, I'm going to do 4 pi, etc. Ten pi. So when we have a very long bless you period, we need to make sure that we count big enough so we can get a whole period on the graph for sure. So that's why I like to do the period first, is it helps me figure out what we're counting by. Okay, so then we're going to find our amplitude because it's easy peasy to spot. So what's our amplitude? 2. Our amplitude's out in front. To find our left endpoint, we take this argument and figure out when it equals 0. So we're going to have our 1/3 x minus pi, and we want to know when it equals 0. So we're adding pi to both sides, and we get 1/3 x equals pi, which means that x equals 3 pi. And again, since this is sine, we're hitting right on 0 anyway, so we can come and put our left endpoint right at 3 pi for our sine part of this. our right endpoint is going to be when that same little argument equals 2 pi. That's a pi. So we have 1/3 x equals 3 pi. So where's our right endpoint? 9 pi. So our right is going to be 9 pi. And when we're graphing our sine, that's enough. Because we know that the other 0 is going to have to be between 6 and 9. And then it's going to hit our amplitude to halfway between. So it's actually going to be right in between for me. So we're going to have a point up here at 2 and a point down here at 2. Yes, dear. Because it's always going to be, so the middle 0 is at the midpoint of these two. And then the high and low points are at the midpoints of these two. So it just winds up at being, 9 pi over 2. Since our period was so long, I counted by whole pies. So I'm just going to plot a few more points so that we can grab our sine curve. 3, midpoint, 1, 2, 3, midpoint, 1, 2, 3, midpoint, just like that. And we're going to connect them up to get our sine curve. Why did I go down? Oh, no, there we go. I see it, because I started from my right endpoint. I was like, what? It goes up here. There we go. So that's our sine. From here, to get our cosecant, any place sine is 0 is where we have our asymptote. So those are the first things we're going to draw properly for cosecant. Is we're going to draw in our asymptotes. So any place sine is 0 is where we have an asymptote. So lots and lots of asymptotes. How could I write down where our asymptotes are located? Yeah. Because it's hitting on every 3n. It's 0, 3n, or 3 pi, 6 pi, 9 pi. So we can say 3n pi, or pi 3n. I don't care what order it's in. Because where our yellow lines are hitting, wherever our sine is 0. I notice here this one's 3 pi. I know this one's 6 pi. I know this one's 9 pi. So we're just kind of writing an expression in how I could get from here to here. So it's 3, 6, 9. It's multiples of 3. So 3n. That tells me it's multiples of 3. From here, to get our graph, we're going to take our high and low points, our kind of maximums, minimums. And we know it's going to get closer and closer and closer to these asymptotes. I don't like that. That's way too chonky. There we go. Because if I was to put these into a calculator, as these got closer and closer to 0, these would get bigger and bigger and bigger and bigger. So we're taking our endpoints, our kind of maximums, and using those to draw our cosecant graph. We're going to take every place that we have an endpoint or a turnaround point or a point of inflection or whatever vocab word you choose for that. Relative maximum or relative minimum. That gives us our graph of cosecant. Last piece on here is to write out our domain and range. What is our domain? Perfection. I'm just going to make my pen a little skinnier because it's really thick. So it's all real numbers, except x cannot be any multiple of 3 pi. If it is any multiple of 3 pi, it's hitting an asymptote. So x can't equal 3n pi, or 3 pi n, or n 3 pi. I don't care what order it's in. You're doing the hard math. Grammar is irrelevant. I genuinely do not care. How about our range? From negative infinity to negative 2, unioned with 2 to infinity. Okay, so it takes a lot of the pieces we have been using over the past 2-3 days and week. Like, we've been graphing these for a hot minute now. But that's why we went so slowly through all of our sine and cosine. Because when we get to secant, same vibe. Okay, we're going to do one more cosecant. Because the one piece we haven't worked in here yet is that midline shift. The domain on that one was everything except where our asymptotes were. It's all real numbers except the asymptote. Yeah, and it will always be like that for cosecant and secant. And cotangent. Okay, this one will be our last one of the day because these do take us a hot minute. And I don't want us to be rushing through it. Okay. So, same vibe. We're going to start with our period to see what we need to count our x's by. We're going to find our amplitude because it's easy peasy. We're going to do our endpoints, starting with graphing our sine. Because cosecant is the reciprocal of sine. What's up? I said, what's up? Oh my gosh, we are shooketh by our notes. We're so surprised. So surprised by graphing a very similar function to the one we just did. Oh my gosh.
Math is a math thing.
Mathing, right? So we're going to start with the period. And that's our 2 pi over b. So 2 pi over, what is our b? 2. So what's the length of the period? Pi. So the length of the period is pi. So we have lots of space. So I'm even just going to spread it out. So I'm going to do even bigger than I normally do because pi is a very small period. I want to make sure we can get everything we need to. 2, 3, 4. I'll do this one as pi over 2. 1, 2, 3, 4, pi. So I'm spreading mine out really far so that we can make sure we get a really good view of the period. Pi over 8. What are you giggling about now? What are we giggling about now? The fact that we have used period in every single problem for the last week? Are we just now giggling about that? period. All right. Oh, those lines do not mean anything. That's called me trying to zoom out. Okay. So I'm counting really big. I did 8 dots to a period. Or 8 dots to a pi. So I'm counting mine very, very big. Let's do our endpoints. So we want to, actually, first thing I'm going to draw is I'm going to draw my new midline. Because this whole thing has gotten shifted up 2. So we have a new midline up at 2. Before I start trying to do endpoints, I like to draw in that new midline, because otherwise I forget. And I just start trucking along right on the x-axis. I forget that so frequently. The number of times I've had to redraw these graphs in my notes because I forgot to shift the midline, it's a little sad. Okay, now we're going to do our left endpoint, which is where our argument, that 2x minus pi over 4, where that equals 0. So that tells us that 2x equals pi over 4, which means our left endpoint is when x is what? Careful with our dividing in fractions. I've heard the same mistake from 2 or 3 people. 1/4 divided in half is 1/8, pi over 8. So our left endpoint happens at pi over 8, which if you expanded out your graph like I did, happens right there. And it's on our midline. So we have to have that shift. So our left endpoint is at pi over 8. Then we're going to do our right endpoint. Very similar vibe. It's when 2x minus pi over 4 equals 2 pi. So it's the same vibe as when we did it with sine. Same pattern. So we know what happens when 2x equals 9 pi over 4, because we're going to common denominator and simplify that way, because I don't want to deal with 2 1/4 pi. Ugh. So our right endpoint happens at where? 9 pi over 8. So just past 1 pi. So our right endpoint happens just past 1 pi. Ooh. What's our amplitude? 1. It's just normal. There's not one written there, so our amplitude's 1. So we know when we're looking up here at our graph, we have our midpoint. Oh, good, it's 8. 1, 2, 3, 4. That's going to be where our other 0 is. It's going to go up 1 and down 1 to get our sine. So this is kind of our basic initial period of sine, which helps if I can actually connect my dots. So that's our primary, like our main period. We're going to repeat it out. So that we can use it to make our graph. So we're going to start with all of these reciprocal functions. We're going to start with graphing the main function. Then we're going to do our asymptotes wherever it hits 0. So every place that we're hitting our midline is where sine is 0. So every place where we hit the midline is our asymptote. So it's been like hitting on the x-axis the last few, but it's hitting the midline is where the issue happens. Where are the asymptotes happening? I'm going to bring it down here to write it. Where's our first asymptote?
Right there.
Pi over 8. It's happening right at that left endpoint, right? And how frequently does it happen? Yeah. So what it's actually going to be is it takes our period in half times n. So when you have these funky ones, the asymptotes happen at half the period plus your endpoint. And you can use either endpoint because they're multiples of each other, but it's the endpoint plus half the period is our weird asymptote thing. I'm not going to ask it super frequently, but just since we're here. So that's why I color-coded it. It's our half period times n plus our endpoint. So let's put our cosecant in here, and then we'll be done. So any place we have a high point, low point, that's where we're going to start our dot. So any place that was a peak or a valley, a extrema, a point of inflection, a kind of vertex thing, however your brain chooses to name that guy. Yes, ma'am.
Is that a minus sign or
On the asymptote, in between the 1/8 and the 1/2, it's a plus. Right there, Belson? Okay. Just wanted to make sure when you say there, of the 5 gazillion things I have, that I got to the right one. All right. Oop, wrong way to go. So I'm going to put these on here, but that's our last one for the day. Okay. So again, they're weird. They take some time. We're going to be working through these for most of the rest of the week, every day except Friday. Okay, so we're going to keep, Friday we're going to start looking at story problems that use the trig functions. Okay, so we are looking at the chapter test, me and the other DC teacher. Because there's so much stuff in this first chapter, we might split it into 2 days. So it could be a Thursday, Friday chapter test, just because there's so much stuff. Okay, not this Friday, next, like the chapter test. I'm talking the end of thing chapter test. The unit exam, it could split into 2 days because there's just so much stuff. In your email, you should have gotten from indiana.edu, from IU. You should have gotten an email to register for this course through the IU portal. You do need to do that. Okay? So go check your school email or go to this link down here. You need to register for this course to get the IU credit. There's only one person registered so far for the dual credit course. Okay? So before Friday, you need to do that. To get the IU credit, you need to do that. You should have a link in your email from acp@indiana.edu. And I will continue to put that up at the end of the period all to tomorrow and Thursday because I use the same slide deck. So I will remind you. Okay? The homework for this is a packet instead of book pages because it's graphs. It's in the tray on your way out. The DC, make sure you grab the DC Precal one. And it's for today, tomorrow, Thursday. So, like, it has tangent, cotangent, secant, cosecant. We're going to get through them all this week. Have a great rest of your day. Happy Tuesday, mate.